Dimensional data density and physicality, a theoretical analysis of cross-dimensional object behavior. Under encoded equilibrium. My name is John Swygert. I am a scientist, a researcher, and an author, and I am the author of the Swygert theory of everything AO. Today I want to explain one of the most important theoretical models in the encoded equilibrium framework. The idea that physicality itself is not a fixed property, but an emergent behavior that depends entirely on the relationship between an object's internal information density and the bandwidth of the dimension it occupies. In other words, solidity, mass, and physical presence are not absolute. They are the byproducts of a deeper informational interaction. In classical physics, we tend to think of matter as inherently solid. A rock is solid because it is made of atoms arranged in a rigid lattice. A liquid is fluid because its molecules slide past each other. But under encoded equilibrium, an object's solidness is not simply a feature of its composition. It is a feature of the dimension it resides in. Every dimension has a finite capacity to hold information. That capacity is what I refer to as dimensional bandwidth, and it determines how much structured information per unit volume can be expressed as localized physical form. Inside that dimension, every object carries some degree of intrinsic data density, the amount of organized information encoded within its structure. High coherence, low entropy, and high-order internal organization produce high intrinsic data density, or high IDD. Low coherence produces low IDD. When IDD is compared to the dimensional bandwidth, it produces a ratio that dictates physicality. If the object's IDD is small compared to the bandwidth of the dimension easily accommodates it. If the object's IDD is too large relative to the dimension's capacity, the dimension forces the object into a more compact, crystalline physical state. This threshold behavior determines whether something appears physical, semi-physical, or non-physical from the perspective of an observer inside that dimension. This is why encoded equilibrium treats physicality as a function, not a constant. That function depends on the ratio between internal data density and the capacity of the dimensional rule set. When the ratio is low, an object may appear ghost-like, fluidic, or diffuse. When the ratio crosses a critical threshold, the object solidifies. The dimension cannot host that much information in a diffuse form, so it crystallizes it into solidity. This threshold model also explains why objects may invert their physicality when crossing between dimensions. Consider an object that is barely physical in its home dimension. If that dimension has a very high bandwidth, its high-order internal structure still remains below the threshold. But if the object transitions through a wormhole throat or a translation layer into a dimension with lower bandwidth, the ratio increases. That same object, unchanged internally, may now exceed the threshold. Without doing anything to itself, it becomes more solid simply because it entered a dimension with a lower capacity. This is what I call physical inversion. A non-solid object in one dimension can become fully physical in another. The reverse is also true. Something completely solid to us could become almost non-physical if it entered a dimension with greater bandwidth. This entire effect is a natural consequence of information density mismatches. It is neither mystical nor arbitrary. It is the logical result of encoding rules. Now, when an object actually transitions between two dimensions with different information capacities, it must undergo reindexing. The encoded equilibrium of the substrate must recalculate the object's internal structure under the rules of the new dimension. The portal or wormhole throat acts as a translation layer where this reindexing happens. During that reindexing, energy leakage is unavoidable. The mismatches between possible microstates in the origin dimension and the available microstates of the destination dimension create spillover. That spillover produces characteristic signatures in gamma radiation, terahertz frequencies, and microwave bands. High IDD structures reconfigure sharply, generating short gamma spikes. Mid-frequency structural adjustments produce terahertz emissions. Lower coherence adjustments or near-threshold oscillations generate microwave disturbances. All of these are predictable, falsifiable outcomes of dimensional translation, and they match the kind of energy profiles we observe in certain theoretical and astrophysical anomalies. Mass behaves similarly. Mass is not inherent. It is a measure of how strongly an object's encoded information couples to the geometric degrees of freedom of that dimension. When IDD relative to bandwidth increases, effective mass increases. When the ratio decreases, effective mass decreases. This means dimensional translation naturally predicts apparent mass variability. A traveler entering a lower bandwidth dimension may appear heavier or more massive. Entering a higher bandwidth dimension may appear lighter. Conservation laws still hold, because each dimension has its own internal rule structure. What changes is the way the dimension interprets the encoded information. This framework is not isolated. It aligns with several major ideas in theoretical physics. In holographic duality, the encoding of high-dimensional information onto a lower dimensional boundary is limited by that boundary's capacity. In Kaluza-Klein models, higher modes in compact dimensions manifest as heavier particles when projected into lower dimensional spacetime. In brane world scenarios, bulk information appears differently on branes depending on how the geometry is warped. All of these models implicitly depend on capacity limits and threshold behaviors, the same principles that govern data density and bandwidth in encoded equilibrium. Because this theory is information-based, it also generates clear, testable predictions. Objects with fixed IDD should appear with different effective masses and different degrees of physicality, depending on the bandwidth of the dimension they occupy. Cross-dimensional transitions should generate radiation leakage in frequency bands determined by the degree of mismatch. High IDD objects in low bandwidth dimensions should collapse into symmetric, energy-minimized geometries. These predictions can be simulated in lattice models or explored through analog laboratory systems where information density and capacity constraints can be engineered. The broader message is simple. Physicality is not fundamental, it is emergent. It depends entirely on how much information an object carries and how much information the dimension can hold. Change the bandwidth and you change the physicality. Under encoded equilibrium, this is the mechanism that governs dimensional translation, mass variability, energy leakage, and physical inversion. My name is John Swygert, and this is a dimensional data density analysis under the Swygert theory of everything AO.